Hi everyone and welcome back. In this video, we are going to talk about rationalizing the denominator of a radical function. So, rationalizing the denominator is a strategy that we use in algebra that allows us to manipulate and rewrite an expression so that we end up without a radical in the denominator. The reason why this is so important is because sometimes radicals in the denominator behave irrationally, if you will. So, for example, say I wanted to do 5 divided by the square root of 2. Okay, I have a radical in my denominator. And although this doesn't seem like a difficult problem or really much to write home and worry about, let's take a look at this radical. Let's take a look at the square root of 2. Here's my trusty calculator. Here's 2. And here is the square root of 2. Check it out. It's this long decimal, 1.414, and so on and so forth. It looks like this is all the decimal that I have, but as a matter of fact, that's just an approximation of how many digits my calculator is able to hold. So there's a rounding error happening between all of these values here. So when I'm dividing by a rational expression, oftentimes I have a rounding error. And while this may not feel important to you or your life in the moment, it is very important that we avoid rounding errors at all costs in mathematics, specifically for when we are using our math skills in applications. So let me give you a situation in which would be very important for us to not have radicals in the denominators. So let's say you are a part of a team who is sending a spaceship to Mars. You are an astronaut or an engineer or any aerospace. You work in the aerospace industry, and y'all have to figure out how you're going to send the spaceship to Mars. And the most important way to get there is making sure you have enough fuel, right? So in your calculations, you guys are coming across that there's a radical in the denominator, and not thinking that it's too big of a deal, you let it continue to stay in your expression, and then a calculator, either yours or some sort of supercomputer, is making the calculations to make sure that we can figure out exactly how much fuel we need to get there. Although that calculator or that supercomputer creates a rounding error, which is a big deal and ends up giving us slightly less fuel than we need to actually land on Mars. Well, first of all, you are going to lose your job because you had one job to make sure you got enough fuel to Mars, right? And a pretty big deal because fuel is incredibly expensive, and this is a huge project. But even further than that, so your spaceship doesn't make it to Mars. They run out of gas, they run out of fuel, and they're just out there floating around in space. So we've lost a spaceship, we've lost a crew, we've lost billions of dollars to send this thing into space, and then we don't even get to Mars and grab any data or whatever we're looking for as we're there. There's another awful ending to this story, right? So your spaceship runs out of fuel and it's plummeting towards Mars. However, it ran out of fuel and you're not even able to stop it. Crash, billions of dollars wasted again. Right, pretty big deal. So we don't like to have rounding errors for those types of reasons. It might not be important for you right now, but in the grand scheme of things, when calculations are incredibly important and incredibly precise, we don't want to make errors. So that's why we came up with this strategy to get rid of them, which is called rationalizing the denominator. So in order to rationalize the denominator, we need what is called a conjugate. Okay, a conjugate. And a conjugate is specific to square roots. I'm only going to talk about conjugates of square roots. A conjugate of a square root is either the exact same expression, the identical radical expression, or it's the exact same expression with a differing sign between the terms. Okay, so what I mean by that, so if I was asking to identify the conjugate of this expression here, 1 and minus 3 square root of x. The conjugate of 1 minus 3 square root x would be the exact same thing, except a different sign in the middle. So this is the conjugate of 1 minus 3 radical x. Just like if a more simple example would be 1 minus 3x is your first pair, your conjugate pair would be 1 plus 3x. And we're actually going to look at what happens with conjugate pairs. We're going to multiply these together in just a second. Now, what if there's no plus or minus between them, right? What if you just have 3 radical x? There's nothing else to go on. You've got like a single term. Well, then the conjugate pair would just be 3 radical x. Okay, and now let's multiply all of these together and see if we can come up with something we notice that happens when we multiply conjugates together, because what we're going to need to rationalize the denominator is use the conjugate to get rid of the radical in the denominator. So let's multiply these. 1 times 1 gives us 1. 1 times positive 3 radical x gives us positive 3 radical x. Negative 3 radical x times 1 gives us negative 3 radical x. And negative 3 radical x times positive 3 radical x, well, gives us negative 3 radical x times positive 3 radical x. Simplifying these terms, I see that our middles terms go away, a positive and a negative, they cancel out, and I'm left with 1. Negative 3 times positive 3 is negative 9. Square root of x times the square root of x becomes the square root of x squared. And this ultimately breaks down into 1 minus 9x. Cool. Let's work through the others and then take a moment to reflect and look back and see if we can recognize any patterns. Here's a very similar problem, except there's no radicals in it, right? 1 times 1 gives us 1. 1 times positive 3x is positive 3x. Negative 3x times positive x, or positive 1 is negative 3x. And negative 3x times positive 3x is negative 3x times positive 3x. Simplifying this expression, I notice that my middle terms also get canceled. I end up with 1. Negative 3x times negative 3x is negative 9x squared. And lastly, let's multiply these two radical expressions together using the product property of radicals, right? So the product property of radicals would say that the outside values get multiplied together. So I have 3 times 3. And the inside values, the radicands of radicals with the same index, get multiplied together under one single radical. So this is 3 times 3 times the square root of x times x. Notice that 3 times 3 gives us 9, and x times x under a radical, under a square root specifically, pairs, groups of 2, 2 of a kind, break free, and we're left with 9x. So let's take a look-see here. I notice that as I'm multiplying two binomial expressions, the middle terms always cancel out, and the middle terms in the radical expression had the radical. I also notice that when I multiply, the radical gets removed because a square undoes a square root. I also notice that 3 times 3 is 3 squared. Radical x times radical x is radical x squared. Looking at my binomial times binomial without a radical expression, my middle terms also cancel. I have negative 3x times negative 3x, or negative subtracting negative or positive 3 squared and x squared. So I'm squaring my last term. And I don't have any x's anymore, where I started off with x's. In this last example, I noticed that I have two radical expressions. And when I multiply them together, I don't have any radical expressions at all. This is a property of radical expressions. You will notice that the middle terms always cancel out when you have a binomial. You will notice that the last term always ends up getting subtracted. You'll notice that the last term also ends up getting squared, right? If I really get into it, this is really 3 squared and square root of x squared. Same thing here. This is 3 squared and x squared. My last terms get squared. And they're always subtracted. And then in our monomial type of expressions that are being multiplied together, the radical is eliminated altogether. This is a strategy that we're going to use to rationalize the denominator. So let's work through two examples. Actually, yeah, two examples of rationalizing the denominator. And I'll walk you through the process of actually how to rationalize the denominator. So we're going to need conjugates, okay? Okay, so here is how we actually rationalize the denominator, and I'm going to give you step-by-step breakdown, okay? To rationalize the denominator, I'm going to put how to. Okay, step 1 is going to be identify the conjugate. Of specifically the denominator. This is important because we're called rationalizing the denominator, and I need to get rid of the radical in the denominator, right? So I have to figure out, well, what am I trying to get rid of? I'm going to use the conjugate to get rid of the radical in the denominator. It also says denominator here. Step 2 is going to be to multiply the expression that we are given by a ratio, because the word rationalizing has the root word ratio, by a ratio, which if you don't remember, a ratio is just a fraction, of your conjugate. And lastly, step 3 is going to be multiply and simplify. So let's do 2 examples of how to rationalize the denominator. So here's example 1. Let's do 1 over 3 minus the square root of 2. And I want to rationalize the denominator of 1 divided by 3 minus square root of 2. I have to rationalize it because of this pesky square root. So what am I going to do? I'm first going to identify the conjugate of the denominator. So off to the side, I'm going to say, what's my conjugate of the denominator? I'm going to look at it. And remember, this one has 2 terms. So it's going to be exactly the same, except with a different sign. So it's going to be 3 square root of 2 with a plus sign. I have identified my conjugate. Step 2 says to multiply the expression by a ratio of my conjugate. So a ratio is a fraction. There's my fraction bar, right? And it's going to be 3 plus radical 2, my conjugate, divided by my conjugate. And the reason I'm doing this is so that I am performing the algebraic manipulation of multiplying times 1. Anything divided by itself is technically 1. So technically, I'm not breaking any rules of algebra. I'm just getting very, very clever. And lastly, all I need to do is multiply and simplify. Using the rules of rational expressions, I know how to multiply and simplify these. So let's check it out. When I multiply rational expressions, I multiply the top together and the bottom together. So if I'm doing that, this is going to give me 1 times 3 plus square root of 2, right? Nothing new to see here. I want to make this all one color. 1 times 3 plus square root of 2. And for the denominator, we are going to make sure that we use properties of radicals. So numbers, I apologize, we're going to make sure everything gets multiplied together. Kind of like when we were talking about the conjugates earlier. So it's 3 times 3 is 9. Our middle terms are going to be plus 3 radical 2 minus 3 radical 2. And subtracting the square root of 2 squared. Just did a little double distribution there. Simplifying this, my numerator just becomes 3 plus the square root of 2. The 1 kind of gets eliminated. In my denominator, remember, properties of conjugates is that the middles cancel out. So I have 9 minus square root of 2 squared. Squares undo square roots, so I have 2. And my final result becomes 3 plus the square root of 2. And the square root of 9 minus 2 is 7. Awesome. And now I can see that I don't have a radical in the denominator, which is fine. I can have it in the numerator, but definitely not the denominator because of those rounding errors. Let's do one final example of rationalizing the denominator. So let's do 4 square root of 9 divided by 5 square root of 15. Okay, I want to rationalize the denominator for this problem. And again, my first steps were to identify the conjugate. So let's think about it. What is the conjugate of the denominator of this expression? Well, I got to look at my denominator first and be like, oh, there is no sign between this, so the conjugate is exactly itself. My conjugate for this problem is going to be 5 radical 15. Step 2 then says to multiply the expression by a ratio of my conjugate. So again, I'm going to set up an expression with a ratio, and I'm going to put my conjugate on the top and my conjugate on the bottom. And now I can use the laws of algebra to multiply and simplify. I'm in radical land right now, so to perform this algebra, I know in radical land that the numbers on the outside of the radical multiply together and the numbers on the inside of a radical multiply together. So what I end up with for my numerator is 4 times 5 times the square root of 9 times 15, all divided by the same type of idea. 5 times 5 on the outside and the square root of 15 times 15 on the inside. Now, I'm going to do a little bit of manipulations here. I'm going to leave this for a second, the 4 times 5, and I think you'll see this in a second, so just bear with me. I know I can simplify some things right now, but I'm going to leave it as 4 times 5 times the square root of 9 times the square root of 15. For my numerator, I use my product property of radicals to break it up. And the denominator is going to be 5 times 5 times 2 of a kind break free, groups of 2 break free, 15. The reason I did this is because I know the square root of 9 is 3, so I have 4 times 5 times 3 radical 15 in my numerator. And my denominator, I have 5 times 5 times 15. Okay. As far as elimination goes here, I can see that, well, I can certainly cancel 5 divided by 5. And 3 goes into 15 5 times. And these all became a 1 secretly. So now my numerator becomes 4 times 1 times 1 times 15, or 4 radical 15. And my denominator becomes 5 times 5, which is 25. Now, there's plenty of different ways that you can actually perform this particular problem. I just chose to leave the square root of 9 because I knew that it was a perfect square, so it would break free.